Second type of important elementary functions are exponential functions because they appear in so many models, in growth models like investment models, population growth models, or in decay models like radioactive decay or temperature decay. So these are very natural functions and they are of this form. So x here, variable, actually it's the input, and a constant base. So the power is variable, but the base is constant. So as an example, we can have 2 to the x, and this function has a graph like this. But it grows exponentially fast. So this is x, this is y. It will grow very fast. When x is 0, let's say x is 0, then 2 to the x will be 2 to the 0. The 0 power of any number is 1. So it's going to be this point, 0, 1. If x is 1, then it's going to be 2 to the 1. But the first power of any number is that number. So it's going to be this point. Okay. And then if you give bigger values like 2 to the 2, that's 4. If you give x equals 3, then 2 to the third, 8. As you see, it grows very fast. If I give, let's say 10, 2 to the 10, it will be just, impossible to graph this function. And if I give something smaller, let's say x equals -1, then 2 to the -1 is like 1 over 2, which is 0.5. So it's something here, let's say. This point at -1, we are going to get 0.5, 1 over 2. Okay. And when we look at these exponential functions, we have a constant base, okay, but the power is changing. That's our input. And as I said, these are very natural functions. They really appear in so many quantities when we, keep track of their changes. And one other thing I want to say here is the domain. The set of, remember, domain is the set of all inputs of the function 2 to the x. If you look at it, you can plug in any number here. You can go from any negative number to any positive number, and it will give some value. So the domain is anything in between -infinity and +infinity, or sometimes we just say R, or, which is the notation for all the real numbers. And the range, which is the set of all outputs, so if you look at the set of all outputs, as you see from the second column of the table, we are getting numbers which are all positive. And you can also see, remember, the horizontal axis, this is the domain axis, and the vertical axis is the range axis. What do I mean by this? So if you know the graph of your function, and if you project this onto the domain axis, you will find the domain. Well, you can see maybe it is going too fast here, so you may say, okay, I don't see anything projecting onto this part. But well, if we had a bigger graph, that's our only, that's our lack of technology here. But there is no obstacle that, I mean, we cannot input any bigger number here. We can input any bigger number. It's going to give a huge number anyway. So if we had a bigger graph here, it would just cover up all the domain axes. So the domain is from minus infinity to plus infinity. And the range axis is the projection onto the vertical axis. So from this picture, you can see it's going to cover up all the positive numbers in the range axis. So the range of a basic exponential function is anything from 0 to positive infinity. Okay, so 0, we cannot obtain 0 from any exponential function, but it can get smaller and smaller. As you can see, 1 over 2 will be 1 over 4 at 4 minus 2, and then 1 over 8 for minus 3. 1 over 8 is something like 0.125. Well, you can keep going like that. 2 to the minus 1 million. You know, it's going to be something very, very small, very close to 0, but it's not going to be 0. Anyway, so these are, so the range of exponential functions like these, it's going to be all the positive real numbers. Okay. Well, of course, you can change the base to some other base. Let's say 10 to the x. This is another exponential function. Or you can make the base 3. 3 to the x. This is another exponential function. Or you can have another exponential function. Let's say in the real life models, we may have some other numbers. Let's say like 0.1507 to the x. This may be, I mean, this is another exponential function, but in the real life, we may have less round numbers, you know. But of course, in our course, we are going to work with round numbers just to, you know, make things easier. But you should imagine that, you know, in the real life, the numbers will be less round. But anyway, so whatever the situation is, you know, we will have some numbers anyway. So we need to know how to deal with these exponential functions. We need to know some properties of them. That's what we are doing here. Okay. The logarithms are inverses of exponential functions, but we are going to talk about them after the inverse function stuff. I'm going to talk about it. And the third type of functions are trigonometric functions. So the trigonometric functions are, they arise a rotational change, something, you know, rotating and its projection. Okay. So first of all, let's start with some of the basic trigonometric functions, like sine of x. They all come from a right triangle. So if we have a right triangle means one of the angles is 90 degrees right angle. And let's say one of the angles is x. So let's say this is A, this is B, this is C. Okay. So A is hypotenuse, B is opposite side, C is adjacent side. So sine is the opposite side over the hypotenuse. Okay, this is sine of x. And then cosine of x is the adjacent side over hypotenuse. Okay, so you could also write like opposite side to x over hypotenuse. And you can say that cosine is adjacent side to the angle x over hypotenuse. Okay. So since we have a right triangle here from the Pythagorean theorem, what do we have? A square equals b square plus c square, right? This is a very basic uh, theorem. You know, Pythagoras, he's the first philosopher ever known in the history. Actually, the history starts with the Greek history, and Pythagoras, he is one of the first philosophers, actually, maybe the first one even, that is known to the human history anyway. So this is a theorem known by his name. And if you take this and divide it by a squared, you are going to have 1 equals, you know what is b over a here? We just wrote it. It's sine, right? B over a is sine of x, but we have it square, plus, and what is c over a is cosine. Cosine of x square. So sine square plus cosine square is equal to 1. That's a very important identity we need to know. So we need to know that sine is opposite side to x over hypotenuse, cosine is adjacent side to x over hypotenuse, and the square of sine and cosine of the same angle x, if we sum them up, is equal to 1. This is very important, which comes from the Pythagorean theorem. And then there are these other identities, tangent and cotangent. These simply come from sine, the ratio of sine and cosine. So sine and cosine are the basic ones. The other 4 trigonometric functions, they come from these two. Cotangent is cosine over sine. Okay, so we need to know these two also. Sine over cosine is tangent, cosine over sine is cotangent. You could also say from the right triangle we have drawn. Okay, not a nice one. So this was A, this was X, this was B, this was C, right? So what is tangent? It's sine over cosine. So you can say B over A over C over A. And if you flip this and multiply, what are you going to get? This is going to give B over C, right? Which is opposite over adjacent side. And cotangent, this comes from C over A over B over A. If you flip the denominator and multiply with the numerator, that's going to give C over B. But shortly, it's cosine over sine, okay? And the other two functions are secant, that's very quickly obtained as 1 over cosine. Okay, so I'm skipping the other stuff, but you can write it from our definitions. You can write cosine, which is C over A, and then you can flip and multiply by 1. You are going to get what? A over C, hypotenuse over adjacent side. But we don't need to memorize that much. All we need to remember is this: secant is equal to cosine. And then there is this last one, cosecant. And that's, as you can imagine, it's 1 over sine. Okay, so secant is 1 over cosine, cosecant is 1 over sine. So as you see, once you know sine and cosine, you can get the other 4. Because why? Tangent is sine over cosine, cotangent is cosine over sine, secant is 1 over cosine, cosecant is 1 over sine. Okay, so the important thing here is to know the sine and cosine. The other relation between sine and cosine, as you have seen, sine squared plus cosine squared is 1. That corresponds to a rotation, which I've been talking about. Okay, this is supposed to be a unit, a circle. I mean, this is supposed to be a circle, not a round circle, which the one I draw isn't that nice. But let's say you have a radius 1, okay? This point is 1, 1, 0. This point is 0, 1. This point is minus 1, 0. And this point is 0, minus 1. Then, if you draw a right triangle here, this radius is also 1 because all the radius is 1 here. This is 1. This is 1, okay? And this is also 1. So this is also 1. The hypotenuse is also 1. So if you draw the angle here, x, then remember, if we have the right triangle with side A, B, C, x, and then sine x is B over A, and cosine x is C over A. Remember, we had the Pythagorean theorem, a squared equals b squared plus c squared, and then if you divide everything by a squared, we had b over a squared plus c over a squared, and then that was giving us 1 equals sine square x plus cosine square x, right? So the right triangle here we have the hypotenuse 1. So this side, the opposite of x, this is sine of x. Maybe I should use a different color here to make it better. So let's draw here. This side is sine of x. This side is cosine of x. So this point here is the input is cosine x, the output is sine x here. Okay, so if you have a rotation like this, the projection onto the horizontal axis gives the cosine of the angle x, and the projection onto the vertical axis is gonna give the sine of the angle. Okay, so that's why if you keep moving this point on the unit circle, then you are going to have projections onto the horizontal and the vertical axis every time for the position of the angle x. And then you are going to get some number between minus 1 and 1 each time for cosine and each time for sine. So at most the sine can get plus 1 and at least it can get minus 1. This is also very important to know. And same for cosine. At least cosine can get negative 1 and at most it can get positive 1. Okay, so they oscillate between these numbers. Okay, so the graph of sine looks like this. At 0 it is 0, it can get at most 1, and then it can get 0 again, but can get at least at minus 1, let's say somewhere here, and then it keeps oscillating, coming back to 0, going back to 1, coming back to minus 1, keeps going like this. Or it can go in the other way around. Okay, so it can get at least minus 1, at most plus 1. These numbers are pi. This is 2 pi. This is 3 pi. Okay, this is minus pi. This is minus 2 pi. The top point here is pi over 2. The bottom point here is 3 pi over 2. This is 5 pi over 2. Now, why am I getting these pi's here? So this is the graph of sine of x. So remember, the circumference of the unit circle, unit means radius 1, is what? 2 pi times 1, which is 2 pi. So that corresponds to a full rotation. So 360, a full rotation, 360 degrees, a full rotation, corresponds to 2 pi. This is radians, by the way. This is a unit in angles, radians. So if we have a half rotation, then it's going to be 180 degrees. Then it's going to be just half of 2 pi, half the circumference. If we have a quarter rotation, then it's going to be half of half, or 1/4 of full, which is 90 degrees. Okay, so that's gonna be the thing we are gonna be using. Like maybe in the high school, I'm not sure, you may have seen the degrees like 90, 180, 360, but now we are gonna use radians now. Okay, so we should be used to this. So 2 pi is full rotation, or 360. Pi is half rotation, or 180 degrees. Pi over 2 is a quarter rotation, 90 degrees. Okay, and we can also obtain other angles, like let's say 60 degrees, 45, or 30, which you may have seen earlier. 45 is again 1/2 of quarter, so that's like pi over 4. And 60 is like what? 2/3 of, like 60 is 2/3 of 90. So multiply 2/3 in radians, which is pi over 2, that's going to give pi over 3 radians. And 30 is 1/3 of 90 degrees. So 1/3 of 90 means 1/3 of pi over 2, which is pi over 6. Okay, so you can also obtain these degrees. Well, of course, 0 degrees is going to be simply 0 radians. So we should be used to these things. And the graph of sine, as you see, it oscillates between +1 and -1. It keeps oscillating. Okay, and cosine is in a similar way. So it's here 1. Again, it oscillates between +1 and -1. Okay, it's 0 and then -1, +1, -1. Okay, so this is +1. This is -1. Of course, my picture isn't that nice, but you know what I'm talking about, I'm sure. So this point is pi over 2. This is pi. This is 3 pi over 2. This is 2 pi. So on and so forth. So this is cosine of x. And they keep oscillating between +1 and -1. And as you see, the domain of both sine and cosine are all real numbers. Okay, so you can plug any number in between them. The number you are plugging into sine and cosine means you are plugging an angle actually. So then you have the projection of that angle onto the horizontal and the vertical axis. So the projection onto the horizontal axis will give you the sine of the angle, and the projection onto the vertical axis will give you the cosine of the angle. And as you can see, both of them have same range. They keep taking values between +1 and -1. So that's also very important to know. So this is -1, +1. okay? Because they take all the values between +1 and -1, but they don't take 2, they don't take -2 when they are just sine and cosine. So these two are very important functions now.